The logistic distributions hold an important place in nonparametric statistics. In addition to underlying several important nonparametric methods, they also are often seen as a very reasonable and simple mathematical form for modeling a set of data. Now, if you're not familiar with the logistic distributions, you may be startled when you get your first glance at a logistic distribution. Here's one. If I had not put the title on this distribution, and if it had not been in the context of this particular presentation, you would have looked at that and said that's a normal distribution. A normal distribution adheres to a precise mathematical function, and the fact that a distribution is bell-shaped does not make it normal. What makes it normal is whether it adheres to that mathematical function. So when you see data in which most of the scores are in the middle and fewer scores as you go off to the left and the right tails, the negative and the positive tails, looking at distribution like that doesn't give you reason to state that's a normal distribution. What would give you a reason to state it's a normal distribution is if you superimposed a normal distribution on the data and the fit was very good. But what I'm suggesting to you here is that if you superimpose the logistic distribution, the fit might even be better. So just because data have a certain shape that looks like this, don't assume it's a normal distribution. The properties of the logistic distribution. The logistic distribution is leptokurtic. What that means is that we find a greater percentage of our units in the middle of the distribution than we do with the normal distribution. We also have heavy tails, meaning that we find a greater percentage of our distribution out in the tails of the distribution than we do in the normal distribution. Well, that might seem counterintuitive to you. You might say, wait a minute, how can we have both a higher distribution in the middle and a higher distribution in the tails? Well, that's because there's fewer units in the logistic distribution in between those. So when we define some middle point, like say plus or minus 1 standard deviation, there may be more area in the logistic, and when we define some tail, such as outside of 2 standard deviations, there might also be more in the logistic, but that necessarily means that there are less units in the logistic distribution in that interval between 1 standard deviation and 2 standard deviations from the mean. So the logistic distribution is both leptokurtic and has heavy tails. The parameters of the distribution are alpha and beta. Just as I did not give you the actual function for the normal distribution, I'm not going to give you the actual function for the logistic distribution here, but those of you who are mathematically inclined and have an interest, you can readily find the function for the logistic distribution, and when you find that function you'll see 2 parameters, alpha and beta. This distribution forms the basis for logistic regression. So you'll learn much more about the logistic distribution when you learn about logistic regression, and you'll see those parameters alpha and beta used in logistic regression. So just like there's a variety of procedures that are based on the normal distribution, we have procedures based upon the logistic distribution. There is nothing magical about the normal distribution in terms of basing procedures on that. We can create procedures based on any mathematical function. The mean of the logistic distribution is alpha, and the standard deviation of the logistic distribution is the square root of beta squared times pi squared divided by 3. Here's a comparison of a logistic distribution shown here in red and a normal distribution shown in black. I created both these distributions to have a mean of 50 and a standard deviation of 10. Notice that if you look within one standard deviation, that is from 40 to 60, that you'll note the logistic distribution has greater area than the normal. Notice the higher peak. Also, although harder to see, if we go out in the tails of the distribution, say 2 standard deviations away, which with a mean of 50 and a standard deviation of 10, that would be 2 standard deviations away would be 30 on the low side and 70 on the high side. So if you go from 30 to 70, you'll notice that the red line is actually above the black line. The logistic distribution has greater area in the tails. Where the logistic distribution has less area than the normal distribution is between that 1 and 2 standard deviations range. I hope that one message you take away from this presentation is that you won't ever again look at data that have a bell-shaped curve and say, oh, that's a normal distribution. You can go ahead and say it's a bell-shaped curve, but whether the logistic or normal fits it better is something that you would have to figure out by comparing the function to the set of data.